Hi everyone, welcome back. I'm still David Wajc, and for this talk I'd like to tell you about joint work with co-authors at EPFL, Buddhima Gamlath, Michael Kapralov, Andreas Maggiori, and Ola Svensson, all of whom are either somewhere in the room or somewhere in the premises. Good, so this work is titled Online Matching with General Arrivals. And let's start by quickly inspecting a special case of this problem, namely the online bipartite matching problem. So the dynamics will be kind of similar to the previous talk, only different objective, of course. So the underlying graph is a bipartite graph. Initially, we only know one side of the graph. And every so often, an online node, a node on the other side shows up together with its edges to its previously arrived neighbors. Okay? An online algorithm has to decide immediately and irrevocably to which of these neighbors to match this newly arrived node. Okay, to which of the unmatched neighbors to match this online node. So we might match along this red edge like so. Another node shows up. We decided to match it like so, and so on and so forth. For the fourth node, we really don't have any choice because both of its endpoints are already matched. And remember, our matching choices are irrevocable. Okay, so neither of these nodes can match to this. Neither of these neighbors can match to this newly arrived node. Ditto for the fifth node. And what we find here is that our algorithm outputs a matching of size 3. Whereas if you look at this input for exactly one hot second, you should see that the horizontal edges give you a matching of size 5. Okay, perfect matching. As usual, we'd like to compare ourselves to this hindsight optimum, and our measure of success is the competitive ratio, which is exactly the worst case ratio over all graphs of the cardinality of the matching output by the algorithm to the maximum matching size. Notice that unlike the previous talk, and more similar to the terminology used in the online matching literature, our competitive ratio will be at most 1, will be less than or equal to 1. So just to make sure we're all on the same page as to what can be done in this model, so the greedy algorithm, which always matches an online node to one of its free neighbors, if it has such a neighbor, will output a maximal matching, and is therefore 1/2 competitive. And unfortunately, no deterministic algorithm can do better. So this problem is kind of boring for deterministic algorithms, and here's why. First online node shows up. Maybe our deterministic algorithm will always match along the diagonal edge, and now another node shows up and only neighbors this matched node. Okay, so we only get the one lousy edge, even though we could have gotten 2. Okay, so now the natural question is, what is the power of randomization by us? Can we do something better than this very uninteresting algorithm? In come Karp Vazirani and Vazirani with an answer to this question, was an absolutely beautiful algorithm, which they called ranking. And this algorithm is so simple and sleek that I can describe it in exactly two lines and a little bit of animation magic. So as our first step, before any online node shows up, we'll permute the offline nodes like so. OK, some of you missed that, so let me go over this again. As a first step, we'll permute the offline nodes like so. OK, perfect. Spent so much time on this animation. Someone at least should see it, right? OK, good. As a second step, basically what we'll do, whenever an online node shows up, we'll just greedily match it to an unmatched neighbor, breaking ties in favor of the highest unmatched neighbor into this random permutation. OK, so it's greedy plus some randomized tie-breaking rule. So maybe this is some run of this algorithm after we've already computed this permutation. OK, so as I said, this is basically just the greedy algorithm, albeit with a randomized tie-breaking rule. So it's at least 1/2 competitive. How much better than 1/2 is it? Well, as KVV showed, this algorithm is 1 - 1/e competitive. And this is optimal for all online algorithms. So they've completely solved this problem. Good. Over the years, people have studied all kinds of extensions of this problem to weighted variance and B-matching variance and what have you, most of which were motivated by internet advertising. Bless you. And for all of these problems, all of these extensions, we know that greedy will give you a competitive ratio of 1/2. And 1 - 1/e is the best you could hope to get. And for most of these, we know how to get it. So as I said, most of these extensions of online bipartite matching were motivated by internet advertising. So the offline nodes are advertisers. The online nodes are ad slots. And the Google or whoever decides what ads to show you. But hopefully, I'm not going out on a limb at Fox by saying that there are better reasons, or at least other reasons, than maximizing Google's bottom line as a good reason to study theory. OK, maybe only one person found that amusing, but fine. I think this is a good point. Also, hopefully, we're all aware that there exist non-bipartite graphs out there. OK, so the question we study in this work is, whether or not greedy is the optimal algorithm for online matching under more general arrivals. We have two notions of more general arrivals, so I'll mention both. The first is general vertex arrivals. So now the graph need not be bipartite, and vertices arrive one after another, together with their edges to their previously arrived neighbors. And what an online algorithm has to decide is when a node shows up, immediately and irrevocably decide whether or not to match it to one of its previously arrived neighbors, or drop all of your edges to your previously arrived neighbor. Okay, notice that this generalizes the KVV model, where the first nodes to show up are the offline nodes, followed by the nodes on the other side. Okay, even harder still, you could consider edge arrivals, where hopefully the model is clear just from the name, but if not, let me quickly double check we're on the same page. So the dynamics here are that edges arrive in some adversarial order, and whenever an algorithm has to decide, immediately and irrevocably, take it or leave it. Do I add this to my matching, assuming I haven't already matched one of the endpoints or both? Or do I drop this edge forever? Okay, so before I tell you kind of what's known about this problem, about these more general arrival models, I'd like to stress that these are, in some sense, require some kind of paradigm shift. Require different ideas. In particular, for bipartite graphs with one-sided vertex arrivals, as I said earlier, greedy with some randomized tie-breaking rule, in particular ranking, allows you to beat a competitive ratio of 1/2. Okay? However, for these more general arrival models, this is no longer the case, as can be shown by this very small and simple example, which is implementable and feasible in both models. So first node shows up. Basically, you see the edge 1, 2. If you're greedy, it doesn't matter what your tie-breaking rule is. You're taking this edge. Okay? Why is this problematic? Well, now, in both arrival models, you can have an edge that shows up incident on 2 and another edge incident on 1, and you find out that opt was 2, but you're stuck with this one lousy edge because you decide that I don't care. If I have an edge that I can match, I'll match. Okay? So we have to be explicitly non-greedy. Okay, so we need some new ideas. In particular, this means that any kind of generalization of ranking, ranking isn't quite defined for general graphs, but any which way you generalize it seems to require some greedy choice plus randomized tie-breaking rule. Okay, so essentially for these models, ranking is just greedy. And I'd like to mention that at least the question of general graphs was studied at least so far, was suggested at least by Karp et al. And if you look at the original paper of KVV and you skim to the last page looking for some juicy open problems, you'll find that they asked specifically this: is ranking an optimal online algorithm for the non-bipartite case? Okay, so for general vertex arrivals. And as I argued earlier, this means that they were basically asking, hey, is greedy the optimal algorithm for the non-bipartite case? Okay, so what's known about this problem? Well, first of all, we know this problem is strictly harder than the bipartite one-sided vertex arrival of KVV, and both of these problems have upper bounds or hardness results that are strictly harder than 1 minus 1 over e. Okay, so we cannot do 1 minus 1 over e, but can we do better than 1/2? Just get anything above the greedy algorithm's ratio. And despite a lot of work on this problem, the only positive results we have are under all kinds of relaxations and assumptions. And at least some of these works motivated these relaxations and assumptions by saying, hey, online matching under edge arrivals at least seems very, very challenging, right? Or at least beating the greedy algorithm in this model seems challenging. And for our first result, we show that it is not actually only challenging, it's absolutely impossible to do better than greedy under edge arrivals, under adversarial edge arrivals. Okay, so there is no 1/2 plus constant competitive algorithm for online matching under adversarial edge arrivals. On the flip side, we give a nice positive result, which says that online matching under vertex arrivals, even in general graphs, admits a 1/2 plus constant competitive algorithm. Good, so hopefully we'll give you one more line so you can parse this. First result says for edge arrivals, the best algorithm is essentially greedy, up to little order of 1 terms. The second result says for vertex arrivals, you can do something better. Okay, so for the remainder of the talk, I'm going to give you pretty much the entire proof of result 1. Maybe a little unusual for Fox talk, but modular calculations, you're going to see everything. Okay, and then in the last few minutes, I'll try and give you like the high-level ideas that helped us get result number 2. Okay, edge arrivals, again, remember, edges show up one after another. an algorithm has to maybe, using some random choices, decide whether or not to take this edge into its matching. Okay, so instead of showing hardness results for randomized algorithms, we're going to show hardness results for fractional algorithms. I'll tell you in a second why this ties into our problem. But first, let me just make sure we're on the same page as to what I mean by fractional algorithms. So an online fractional matching algorithm is one that, upon arrival of edge E, assigns this edge some value xe, such that the x's are in the fractional matching polytope. Okay, so all these x values are non-negative, and for every vertex, if you sum over all of its incident edges x value, you get a value which is at most 1. Okay, if these xe's were binary, right, 1 if you're in the matching, 0 if not, this first constraint is exactly the matching constraint. Okay, so we're just relaxing the integrality constraint. Okay, why, sorry?
Why do you call this a hardness result? It's an unconditional.
Hardness result is, I mean, I don't want to say lower bound, because the way we phrased it, it's an upper bound, and that's just confusing, so I'm going to stick to the hardness result if that's fine, Yuval.
Hardness always implies that you're making an assumption.
I'm not making any assumption. This is an information, okay, so I'll maybe point well taken. I'll just stress out, this is not assuming P versus NP, assuming anything UGC or your favorite conditional core of a conditional hardness result. This is going to be an information theoretic lower bound, or hardness result. Okay, so why do we care about proving impossibility results for fractional algorithms? Because of a simple, easy observation. If you have a C-competitive randomized algorithm, well, there exists a C-competitive deterministic fractional algorithm A prime. This deterministic fractional algorithm need not be time efficient. Doesn't matter. We're going to show information theoretic hardness. Spend as much time as you want. You're not going to do better than 1/2. And by this simple observation, or at least it's contrapositive, you'll find that this implies that there is no better than 1/2 competitive algorithm, randomized algorithm. Okay, so quick proof of this observation in case you don't immediately see it. The marginal probabilities of algorithm A matching E, let's call PE this marginal probability, these are a fractional matching. Right, they're clearly non-negative. Probabilities are non-negative. We're all on the same page here for sure. And in addition, since V is matched at most once in expectation by the randomized algorithm A, the first constraint is satisfied by linearity of expectation. Right, sum of these PEs is exactly, well, I guess in this case, is exactly the probability that V is matched. Okay, so again, just to recap, hardness result for deterministic fractional algorithms implies the same hardness result for randomized algorithms. Good. So here's, any questions? Okay. Our approach here will be to use prefix hardness and LP duality as advocated by Azar et al. And as you saw forward reference from the previous talk. So let me tell you exactly what I mean by this. So again, we're showing hardness result for fractional algorithms. And we're going to give this fractional algorithm a heck of a lot of power. In particular, we're going to tell it what the graph is. Okay. We're also going to tell it in what order the edges are going to show up. This is the first edge, this is the second edge, this is the third edge. So some of you are smirking or look confused, or something's up, right? Like this is BS. This is an easy problem. You can get to one competitive algorithm if this is the setup. So what's the one way we're going to make life difficult for the online algorithm? We're just not going to tell it what a time horizon is. Okay? Put otherwise, what we're doing is we're giving it some promise problem. I'm telling you as an online algorithm, the input is either the input induced by the first edge, or by the first 2 edges, or by the first 3 edges, and so on and so forth. Okay? Now, the fact that you don't know at what time the input is going to stop means that you better be competitive at every goddamn point in time. Okay? So again, if you have a C-competitive fractional algorithm, you have to be competitive for each prefix. Remember, you're not allowed to change the x values. Okay, so once an edge shows up, you have to assign it some value so that you've covered this prefix so far. And what's nice about this observation is that you can actually write this as a linear constraint, which in particular implies that if you have a C-competitive fractional algorithm, then you have to have a solution of value at least C to the following LP. We're going to maximize alpha, which will be our competitive ratio, subject to x being a feasible fractional matching. And in addition, for every prefix of the edges, the total x value accrued over this prefix P has to be at least alpha times the max matching in that prefix's induced graph. Okay, that's the overall idea. So now if you give me a graph and an arrival order for its edges, I can give you a hardness result, an unconditional hardness result for online matching under edge arrivals. Okay? Kind of unfortunately, what we want to do is get some asymptotic claims and say something about asymptotically large graphs. So to get something from this formally, maybe you'd have to symbolically solve the LP, which is a bit of a drag. So instead of doing that, we provide a dual solution of value C. So we provide the solution of value C to the dual LP, which upper bounds the opt of the primal of this hardness LP. And from that, and from the previous discussion, we find that there exists no C plus epsilon competitive algorithm for any epsilon. Okay, if you have. Okay. Great, so putting all of this together and maybe picking your hard family of graphs judiciously, what we find is that for any epsilon greater than zero, doesn't matter if it depends on n in any way, there exists no better than 1/2 plus 1 over 2n plus 2 competitive algorithm. Actually, forget the constants. There exists no better than 1/2 plus order 1 over n competitive algorithm. Okay? Notice this was even for fractional algorithms, even in bipartite graphs, even if I tell you more or less what the graph is. Okay, so it's really bad news for this problem. For the next few minutes, let me briefly tell you some ideas for the vertex arrival idea. And when I mean briefly, this is really going to be the tip of the iceberg. So in this model, again, we have vertices that show up. And when a vertex goes up, it reveals all of its edges to its previously arrived neighbors. And we have to decide who to match them to. So our starting point will be a online fractional matching algorithm of Wang and Wang, who showed out to beat a competitive ratio of 1/2. And of course, the first natural question is, can we round this without losing throughout, right? Can we match each edge with probability roughly, I guess with probability exactly XE given by the fractional algorithm? Okay, this would give us a 0.526 competitive algorithm. Unfortunately, in general graphs, this is too much to hope for, because in general, a fractional matching can be 3/2 times larger than an integral one. And so if you want to be able to round fractional matchings in general graphs, in general, you have to lose a 2/3 term. 2/3 times 0.526 gives you a competitive ratio strictly less than 1/2. You might hope to be able to circumvent this for maybe bipartite graphs where there is no such problem. But actually, joint work with Ilan from SODA last year shows that this is impossible to do, to round losslessly, even in bipartite graphs with one-sided vertex arrivals. Nonetheless, we're going to try and actually match each edge with probability exactly given by the fractional algorithm. Okay, again, we know this is impossible, but we're going to try and see what we kind of learn along the way. So here's our general approach. When a vertex V arrives, we update our fractional matching using the fractional matching algorithm that's running in the background. And then we pick at most one neighbor U with probability proportional to the XUV value. In particular, we pick up the probability PU, which is XUV over the probability that the algorithm has yet to match node U. And then what we're going to do in the next step is actually check to see whether or not U is free. And if it is, we'll match UV. So if I could implement this high-level approach, I'd be able to match each edge with probability exactly, each edge UV with probability exactly XUV, because steps 1 and 2 are independent of each other. Unfortunately, for step 1 to work, I need the sum of the PUs to be at most 1, because I'm picking at most 1 node always. And unfortunately, for all fractional algorithms that we know that do something non-trivial, this sum can sometimes be greater than 1. Okay, so this is impossible to implement. Well, the natural fix is to normalize by the sum of these PUs if this sum is greater than 1. Okay, maybe, so now we'll match each edge with probability XE over some of these PUs. Okay, maybe we don't lose too much and we still stay above 1/2 competitive ratio. Unfortunately, that's not the case, and we actually lose too much by this normalization. So one natural fix to this is to say, look, in step 2, we realize that sometimes we pick some nodes that were already previously matched. But maybe we still have some neighbors we could match to. So let's just try again. If you picked a node at random, pick this guy, look, oh, damn, you're already matched, I'll pick another one. And then the hope is that the probability of being picked as a second match, or to be a second pick, will increase your probability of being matched enough so that you still get something better than 1/2. Now, the main difficulty here, come on, you'll get there. The main difficulty here is that the neighbors of V might be positively correlated, and so you might not gain anything from the second pick. So to make this a little more clear, let me take this to an extreme scenario. Let's say I tell you that if U5 is matched, all the neighbors are matched. If U4 is matched, all the neighbors are matched, and so on and so forth. Well, in that case, if in step 2 I picked a node and figure out that it was matched, then I have exactly a probability of 0 of matching somebody else. So this is not going to increase anybody's marginal probability of being matched. Okay, so the main technical brunt of meat of this paper is in showing that for the Wang and Wang algorithm, or at least some algorithm derived from their framework, we can bound these positive correlations and still get something better than 1/2 competitive, as the following theorem says. There exists a 1/2 plus constant competitive algorithm for online matching under general vertex arrivals. All right, so I'm a little over time, so let me just leave you again with the conclusion of what we showed, a couple natural open questions, and I'll be happy to hear some more questions if you have them. Thank you.
So, any question?
Yossi.
The first lower bound is only 3 edges, or it's a longer line?
The first lower bound. Oh, sorry. This hardness result for edge arrivals, we need an asymptotically increasing graph because for bounded degree graphs, we know how to get better than 1/2 competitive. So that's why we needed what I was arguing about going to infinity or whatever. Other question? Yes.
Can you say maybe a little bit more about this graph, like how it looks? Does it have a perfect matching sequence? What's off?
This is what the sequence looks like. Thanks for the question. This is great. So what this looks like is basically you have a bipartite graph, n nodes on either side, and we'll show the edges over rounds. And in round I, we'll have a perfect matching between the first I nodes on either side. And actually, if you look at what's going on here, we're augmenting opt by an augmenting path of length 2i minus 1 in every round. I'd be happy to kind of talk about the intuition behind this. I have no proof of why this is hard other than our LP-based proof, which is maybe short, but maybe not super insightful. Not super, yeah. Not super insightful. I think the approach is nice, but it doesn't give insight as to why this particular family of inputs is hard.
Okay, so maybe we can skip next questions and so that the next speaker can come. And okay, thanks again to the speaker.
Thanks, guys.